Hello, welcome to another problem session. Okay, today I have an interesting problem for you. It's a problem in which we will simulate a gear system. So there will be some force that provided by one mass, and another mass will be moving as a result of that, but at a different radius. So it's like going to a lower gear. Okay, so this would be a small amount of movement. This will be large amount of movement corresponding to that. So let's read the problem, and maybe you can try this and then look at my solution once you have found your answer. Of course, this motion will not happen unless M1 and M2 and M and these R's are right values. Okay. So first is maybe when you hang it, you just support it for a while, and at t equal to 0 you let go, and when you let go you find that this one, so this is kind of given, this happens at t greater than 0. This acceleration is pointed downward. That's what we want. Okay. So this can be lifted. Imagine this is a large mass you're trying to lift, what have you. So you want to find out what kind of mass you need. And then there is a question about tensions. So what is the acceleration of this? For A is the acceleration of this will be A2 that way, and this whole thing will be rotating as a result of that with some alpha. It's a rigid body, so everybody's going to rotate the same, right? So A and B can be found in terms of A1. Okay, and now I added this C. That's an important part of the problem. Is let's find what this A will be in terms of everything else. Okay, so this is like everything else. And once you find that, find out the condition, how much M1 I need, so that based on fixed everything else, my acceleration will be greater than or equal to 0. Okay, so like it will be pointed down. Okay, so like a down is plus here. That's the question. Let's address one by one. So for part A, I noticed that M1 is unwinding at this radius. So if that's the distance, so that's the distance along over here is going to move. So this is delta y1. Again, I'm going to use a axis in which delta y1 will be positive. So this will be my axis for this guy, and for this guy my axis will be pointed up, will be positive for this guy, positive for this guy. And for this, if I am going this direction, I'm going to have a positive. I know this is clockwise, but clockwise will be positive for me. Okay, so this distance over here is how much this will be. So that will be delta y1 in some delta t, some duration. Agreed? So I take that as some given, and suppose I know that, then if I look at this guy, is going to, let's use a green, this is going to get lifted by some amount here, same amount, right? If it's delta y1, this is going to be not the same one. I'm sorry, this is not the same amount. This will be, say, delta y2. But if you look at the angle that this guy gonna rotate, this angle is the same as that angle. So this guy is this angle, let's call it angle delta theta, is going to be, whatever this is, delta y1 over r1. But this is the distance that this guy is going to wind up. So this is the distance that one. Although just draw quite a big, let me make it a correction. So make it look the same. So this is, and this is my thread. So delta y2 will be really tiny. You know, delta y2 will be just this one compared to delta y1. So what is delta y2? This is the angle I'm rotated. So that's the angle I pulled up. So this arc distance will be delta y2. So delta y2 will become r1 times delta theta. So delta theta is the common link between all of this, right? So I'm going to now work them out. So delta theta is delta y1 over r equals to delta r1 delta y2 over r2. That will mean if I take a one derivative of this, divide by delta t, divide by delta t, divide by delta t. So this will also, so the omega will be equal to a1 over r1 is a2 over r. I mean, this is v1, v2 over r2, and this would mean alpha, angular acceleration, take a ddt of this, it will give me 1 over r1 a1 equals 1 over r2 a2, and you can see that a2 is equal to r2 over r1 a1, and alpha equals to 1 over r1 a1. So from a1 I know all this. So this is done. How do I get the tensions? So for A and B I'm given a1. Only for C I'm supposed to find a1 in terms of other things, right? So if I look at the tension T1, I just need to work out the equation of motion for this guy. So for B, I look at this M1, and you have a tension T1, M1G is this way, and the acceleration A1 is that way. So this is a very simple equation. The M1G must be bigger than T1 by this amount. So M1G minus T1 equals M1A1. Make sure the signs are all right, because it's accelerating this way, which means this force is bigger than that force. And I don't need to use axis, but you could use axis. We have already said this is my positive y-axis, so you can do y components, but no, not necessary. So T1 is, I bring this guy on the other side, M1G minus M1A1. And A1 is already given, so everything is given here. So this is the answer for T1. Now T2, similarly, if you work out over here, which I'm going to leave that as an exercise for you. So T2, well, let me work that out also. T2 minus M2G will be M2A. And this time I bring it on the other side, plus M2G. So that T2 will be like that. Now on to the most very interesting part, C, and see if I have enough space for it. So I want to find A1, and the way we will find is we got equation for this guy and equation for this guy. Now equation for the pulley, that's where the information must be. So here is a pulley. The T1 is that way, T2 is that way, T1 is that way. Now this T is in the opposite direction to that T because I'm acting on the pulley. Same way with the this T2, the direction on which acting on this guy is up, but over there is down. So these directions are important. Okay, and if this is going at alpha at some instant t, so this is the situation. There are other forces which are there. One is force of gravity, capital mg at the center, and there is another force which you can say normal force from the axle going up. Now we act on a axis that's through the center of mass. So this is the axis through the center of mass. So this is one of the principal axis through the center of mass, and is going this way, and you can say angular velocity is this way and angular acceleration is that way, but that way we are doing positive. We're doing positive direction. So T1 times its lever arm from this axis to that is its lever arm. From here, this axis to that is lever arm. So this is lever arms are very easy to get here. And T1 with that lever arm is in that direction, which is positive. So T1 R1 is positive for torque. T2 is doing exactly opposite, so it's going to be minus T2 R2. For this guy, torque is 0. For this guy, torque is 0 because it's right on the axis, right? And I don't see any other forces, so this should be equal to I about this axis, and times alpha. So I about axis, it says assume to be a thin disk. This frictionless was assumed here because no other force is frictionless. Otherwise I would have another torque from the friction. The axis, this, so look up of a disk through, so this moment of inertia, and that's going to be half mr square, r1 square, because r1 is the radius of the disk. I know there is a little thing over here, but everything is thin, so we can just assume everything is just one solid disk. Not a bad assumption. And then when you go out there, I see alpha is equal to 1 over r1 a1. So this one I can actually convert also into a1. I can convert this into a1. So T1 was this m1 gr1 minus m1 a1 r1 for this guy, and for that guy I get a minus m2, this should be a2, a2 r2 minus m2 g r2. On other side, I have I is half capital M r1 square, and alpha is 1 over r1 a1, 1 over r1 a1, and this a2 is only thing that are different than a, and I can use this a2 equals r2 over r1. So this is r2 over r1. So replace this with r2 over r1 times a1, and I can collect all the a1s, right? So there is a a1 here, there is a1 here, and there is a1 here, and we can bring all of this this side, and then you can solve for a1. So a1 will be, these are the two things that will be left, m1g r1 minus m2g r2, and the denominator will be all positive. See, you're going to have a half capital M r1, because this one of them cancel out, and there is m1 plus m1 r1, and this one will be plus m2 r2 over r1, r2 square over r1. So that's the a1, and we want to find out when this will be greater than or equal to 0. So denominator is, so this is one of the answers, and when this will be greater than or equal to 0? Well, denominator is always going to be greater than 0. So this is numerator by denominator, and denominator is always greater than 0. That means I can answer this question just by looking at the numerator, which means this m1g r1, m1g is common, m1g r1 has to be greater than or equal to m2g r2. And so as long as m1 r1 is greater than or equal to m2 r2, that should be fine. So this is like a ratio of the two lever arms, right? So this is this machine. If you think of this as a machine, then this machine has to have a right amount of mechanical advantage. So this ratio often is called mechanical advantage. You really have to have correct mechanical advantage for it to do what you want it to do, like lift this big weight, M2. So you can see if R1 is very big compared to R2, a small mass can actually lift a big mass in this setting. And this is how the lever action works. We'll stop here, and I'm not going to review the whole problem like I do in the past videos. I will say that this is a very important problem for you to kind of go over and study again, especially what happened here. Okay, so this is probably one of the this argument here is you should try to see if you can follow it. You can do it yourself. Others are not that special, they just follow rules, but this one is somewhere you have to actually focus understanding what happened. And sometimes this kind of situation is called constraint equations. The variables are related, they are constrained, they're not just can be arbitrary value. Okay, talk to you later in the video. Bye.